Okay, hello everyone. It's my real great pleasure to participate in this nice conference. And first, I would like to thank the organizers, Sergey and Vitaly, for inviting me. And today I would like to talk about, polymer microgel, which are surrounded by two-component liquids, oil and water. So as all of you are familiar with that solid nano and microparticles, they are widely used for stabilization of emulsions in the mixture of two immiscible liquids like oil and water. And they act as surfactants, so they adsorb at the interface, and the driving force for the adsorption is the reduction of unfavorable contacts between oil and water molecules. They reduce, in fact, the surface tension. And the degree of immersion of the solid nanoparticles into different liquids in fact, defines the curvature of the interface. So the liquids where the particle is immersed more, stabilize somehow concave curvature, concave shape, and vice versa. But definitely, if we want to create some stimuli responsive emulsions, so the solid particles are probably not the best candidate to do such emulsions because, well, most of them are inert. In a sense, they once they are adsorbed at the interface, it's very difficult to manipulate their stability, their motion within the emulsion on one hand, and on the other hand, if the concentration of the nanoparticle at the interface is high enough, they prevent migration or diffusion of molecules which can be dissolved in different liquids. How to, to make the emulsion more functional? Well, the idea came with the help of microgels. So it was shown some time ago, in particular in a group of Professor Richtering, that polymer microgel, they can also be adsorbed at the oil-water interface, and they can serve as a much more functional and stimuli responsive alternative to solid particles. And what are the microgels? So the microgels in general, it is believed, because it is not proven yet directly, it is believed that the microgels, they have network-like structure inside. And in fact, the homogeneity of the distribution of cross-linking depends very much on the way of the synthesis of the microgel. For example, if we use precipitation polymerization, it's also known that the cross-links, they are inhomogeneously distributed inside. We deal with a much more dense core and loosely cross-linked corona with a dangling chain, etc. But if we prepare our microgel using the emulsion, mini-emulsion polymerization, or some microfluidic technique, so we always we believe that the distribution of cross-linkers are more homogeneous. But like in the case of macroscopic gels, the most spectacular property of the microgel is the ability to swell and collapse in response to the variation of external conditions like temperature, if we deal with, for example, PNIPAM or PVCl microgels, or via changing of pH, if we deal with microgel on the basis of weak polyelectrolytes. Well, in computer simulation, the picture we would see if we can look inside the microgel like shown here in this picture, and this is a swollen state of the microgel. But if we change the environment, if we change the interaction between monomer units, if we switch on attraction between monomer units, we can see formation of dense, collapsed state of the microgel, which is from the physical viewpoint, is a transition from the gas to liquid. So it's a kind of condensation of the microgel upon the change in the solvent quality. Despite the pretty simple chemical structure of the microgel, the physical properties are pretty sophisticated. In particular, it is believed that the liquid-like behavior is characteristic at the length smaller than the mesh size, where the subchain don't feel connectivity into the network. And if we, for example, address to the theory, I'm theoretician, in polymer science, and if we address to the theory of polymer liquids, so this can be described by a famous expression which was derived for the first time by Professor Edwards in Great Britain and Professor Lifshitz in Soviet Union many years ago. But if we look at the length scales, which are much larger than the mesh size, the length scale of the whole microgel, it behaves like, we call it soft solid, and it can be described in terms of the formalism of elasticity theory, and the elastic moduli are pretty small. They depend on the length of the subchain. The longer the subchain, the softer the microgel. If we adsorb such microgel at the interface, so the driving force for the adsorption is the same like in case of the solid particles. So the subchains which are adsorbed in the interface, they just shield unfavorable contacts between different liquids. But in contrast to solid particles, the microgel can be deformed. And the degree of the spreading of the microgel on the surface, of course, depends on the cross-linking density and on the surface tension. For example, if the surface tension between the liquids is not so high, we can practically observe the more or less spherical shape at the interface. But when we increase the incompatibility between the liquids, we induce the better spreading of the microgel. So along this line, we have increase of the surface tension coefficient. So we have spreading of the microgel on the surface because during the spreading, more and more subchains and more monomer units go to the interface just to shield very unfavorable contacts between the liquids. Also, the concentration of the microgel influence on the size of the microgel. For example, if we consider the monolayers, so here are 3 monolayers at different compression degree, and we have different cross-linking densities. So loosely cross-linked microgel correspond to the upper row and highly cross-linked to the bottom row. And we see that when the microgel don't fill each other, they have maximum spreading in the area of the interface. So, and if we increase the concentration, so here the line correspond to the depict the decrease of the lateral size and increase of the normal size of the microgels upon compression. So if we just summarize the advantage to use the microgel as a stabilizers of emulsion in comparison to the solid particles, so we can say that the microgel have adaptive shape and volume, and they are very promising candidate to use a stimuli responsive agent for stabilization of emulsion. Yeah, so we can control the stability of the emulsion, and we can vary the size of the droplets. And the second very important issue is the permeability. So we can load the microgel with, for example, with catalytic particles, and we can induce reaction. I will talk about interfacial chemical reactions a little bit later. Very interesting effect was detected for the microgels if both liquids are good solvents for the microgels. So if we look at the, if we look into the microgel and just try to understand how the liquids are distributed within, we found interesting effects that the liquids inside, they can homogeneously mixed within the microgel. So if we look at the concentration profiles, so the dashed line correspond to the concentration profiles of the liquids without microgel, and solid lines correspond to the distribution of the liquids inside the microgel. We have a plateau, which means that two liquids have a constant concentration within the microgel. And what's the physical reason for this? The physical reason is pretty simple. So the presence of the monomer units of the microgel shields unfavorable contacts between immiscible liquids within the microgel. So it means that if the concentration is high enough, they can be mixed. Or, of course, we can also find regime when two liquids are segregated within the microgel, but this segregation will be much weaker compared to the segregation outside the microgel. However, if one of the liquids becomes a bad solvent for the microgel, for example, here the red liquid correspond to the poor solvent, we can see some better immersion of the microgel into the good solvent, and the mixing effect diminishes or even can disappear. The question is how to make this mixing within the microgel better in this case. One of the solutions of such problem is to use amphiphilic microgel. So we introduce two sorts of monomer units into the chemical structure of the microgel. We introduce water soluble and water insoluble, and water insoluble means they are soluble in oil. And composition of the soluble and water insoluble groups can define how much water and how much oil can be uptaken by the microgel. Well, in most of our simulation, we considered symmetric composition because we wanted to get a much better mixing of two different liquids. And we considered two sorts of amphiphilic microgel with random distribution of hydrophobic and hydrophilic units, and with a blockwise distribution. So random means that each subchain of the microgel is a random copolymer, and blockwise distribution means that each subchain is the diblock copolymer. So you can also ask me how to make such a microgel. So in case of the blockwise distribution, we can synthesize such microgel using mini emulsion polymerization when star-like molecules of different sorts can react with each other to form microgel. Indeed, if we put such microgel in the interface, they will be for symmetric composition. We have symmetric distribution of the microgel at the interface in case of random copolymer. And if we look at the distribution of the liquids, they are really homogeneously mixed within the microgel. Here is a quantitative proof of this distribution. And in case of symmetric diblock copolymer, we also have some symmetric distribution of the microgel at the interface. But if we look inside, we can see the kind of microphase separation. So we have regions which are enriched by one liquid and regions which are enriched by other liquid. But I would like to draw your attention that the physical reason for the microphase separation in microgels in interface is completely different compared with, for example, conventional diblock copolymers. I would like to draw your attention that the microgel for which both liquids are good, they are swollen at the interface. And the incompatibility between different blocks doesn't play a role at all. And for example, if you consider at the diblocker polymers, which are dissolved in non-selective solvent, they don't form any microstructure. The microstructure is formed only when the solvent is evaporating from the system. The system becomes dense, and incompatibility between monomer units lead to microphase separation. The driving force for the microphase separation in the microgel is immiscibility of the liquid. So one component uptakes water, one component uptakes oil, and oil and water, they are immiscible with each other. And this leads to the microphase separation. And like in case of diblocker polymers, so we know that the ultimate morphology depends on the composition of the copolymers. If we deal with symmetric diblocker polymers, we always have lamellar. For asymmetric, we can have cylinders or spherical structure. The same is valid for the microgel. So if we take microgel with strongly asymmetric diblocker polymer as a subchain, so we don't have any structure. But if we take, for example, mosymmetric, so 4 units, the total length of the subchain is 6 bits in computer simulation. 4 is for A block, 2 is for B block. And what we see here a cylindrical structure, and what's nice, the cylinders are oriented perpendicular to the interface. Indeed, they need to uptake water and they need to uptake oil, and this somehow controls the orientation of the nanostructure's interface. And for the symmetrical polymers, we have lamellar. Here, lamellar are pretty soft, and we have the kind of fingerprint texture because the lamella bend, and the total shape of the microgel, I mean, the cross-section is more or less ring-like. But this is not the case if we consider the microgel with more stiffer lamellar. And the question which we address to ourselves, so how the lamellar structure changes in monolayer upon its compression. Indeed, if you look at the structure of the individual microgel which is absorbed on the surface, we first of all observe some deformation of the microgel. So as you can see, we have some elongated shape of the microgel on the surface. And the reason is pretty simple. It's a kind of the competition of two symmetries. Well, lamellar structure wants to form some stacking, and this is definitely contradicts with the spherical shape of the microgel. And if, well, flexibility of lamella is not so high as this effect dominates, and the lamellar structure is more or less parallel within the particle, which enforces particle to deform. But then, if we increase the compression of the monolayer, what we can see some linkage of the lamellar between the different microgel particles. And upon further compression, we have development of this linking process. So we observe some propagation of lamella from one microgel to another, and ultimately we have pretty good lamellar structure, of course, with some defects, but definitely it is possible to overcome some defects. And in fact, this procedure and this simulation propose a simple, pretty simple way how we can make the films with the perpendicular orientation of nanodomains. So after compression, we can cross-link our film and make some already materials. And in order to understand how the shape of each individual microgel changes, we colored each particle in different colors, and what we can see is that compression leads to further deformation of the microgels, and they become more and more elongated. How can we use well, such effects? I mean, the effect of the mixing of the two liquids within the microgel. So one of the possibilities is just, well, to use microgel as catalyst in chemical reactions where two different reagents, they are immiscible. So one of them is soluble in water, another in oil. And if we supply the microgel with some catalytic groups, so the two reagents can be mixed within the microgel in the presence of catalyst and trigger reaction. Here is a just scheme of the reaction. I will not go into detail. I don't have time for this. Well, how the reaction work. Just well, in brief. So we have make triple contact between catalyst and two reagents within the microgel, like here. And after having this contact, we recolor the bits, making them product of the reaction, and just then break these links between the particles. Well, now we compare it in computer simulation. We compare the rate of reaction in case of homogeneous or homopolymer microgel and amphiphilic microgel. And what we see, so we here in the beginning we have well, some reactants, and we switch on reaction, and we see some recoloring of the or formation of the product of reaction. And what we can see is that in case of amphiphilic microgel, reaction proceeds faster. So the question we also address to ourselves, what's going on if the composition of the mixture of two liquids is strongly asymmetric? I mean, if we have majority of water and very small fraction of oil. In other words, if we add microgel, so the total volume of the oil is much smaller than the total volume of the microgel. An emulsion cannot be formed under such conditions. The question is how the oil will be distributed in such a system. Well, surprisingly, well, it turns out that the whole oil molecules, which have really very small fractions, they can be concentrated within the microgel. Indeed, if we plot the distribution, the density profile, if we look at the density profile of water, it has practically zero within the microgel, and all water is outside the microgel. I would like just to draw your attention that we have only 5% of oil in the mixture. And what we see that inside the microgel, we have 95% of oil and 5% of polymer. Is it a miracle? No, it's not a miracle, and indeed it is possible. It is possible because when the oil comes into the microgel forms some shell, pretty dense shell around the oil droplet. So we can see this elevation of the concentration of the microgel at the periphery. And the polymer beads or monomer units, they look, which have excess, which forms a shell around the oil droplet, they shoot unfavorable contact. That's why any molecules, they try to go into the microgel, well, to be under very comfortable conditions. Indeed, if we look at the swelling degree of the microgel as a function of the concentration of oil, what we see, so here is the first snapshot corresponds to the microgel in pure water. Then we add oil. It is concentrated inside the microgel, and the shell is formed. So here we have, if we plot the density profile for microgel in pure water, it has normal shape. It's a step-like shape. Then we see some collapse of the microgel with the formation of the shell. And then we have swelling of the microgel if we increase the concentration of oil further. But in all cases, the shell is stable. So the driving force for the migration of oil into the microgel is just reduction of unfavorable contacts. If we look at the computer simulation box and, if you study the behavior of ensemble of the microgel particles, what we can see here, so we can see here microgels in pure water, then we add oil which is fully absorbed by the microgels, but further increase of the oil leads to the aggregation of the microgels. They first form some kind of dimers, then these dimers transform in trimers, etc. Upon further increase of the oil concentration, we arrive to the formation of the emulsion droplets, which are stabilized by the microgels at the periphery. Experiment. It is very funny. So we can prove this concept even using macroscopic gels. Well, in order to prove it, we consider it two liquids, so water, and as the oil, we consider it octanol. They are both good solvent for Knipan gel. And here in the left picture, we have just stability of two immiscible liquids, so phase separation of oil and water. In the second picture, we have microgel which swells in pure water. But if we take this microgel and put it into this two-phase liquid, what we observe complete release of water from the microgel and full absorption of the oil. I would like to draw your attention that the fraction of oil is not so high. So, and what we can see, even by eyes, that the microgel surface is different compared to the surface of the microgel swollen in water. The kind of the shell is already seen in the case of the macroscopic gel. Now,
Igor, your time is up.
This is one of the last slides. So now if we look at the microgel, so what we see for the microgels, we see that the hydrodynamic radius and duration radius, they both decrease with the increase of the concentration of the oil. And if we look at the ratio of these two parameters, so we can see that, indeed, in the beginning, we have the structure like fuzzy sphere. So we have, because the microgels, they were synthesized using precipitation polymerization, but then with the increase of this ratio, we go to the regime of the solid spheres, and we are really close to the vesicular structure, which is also the proof that the internal structure of the microgel changes upon the uptake. Similar results are obtained in computer simulation as well. So in conclusions, it's really short. So the microgels can be used as efficient and functional stabilizers of emulsion, in particular as a mixture of two immiscible liquids. And they also can be served as scavengers of substances which are dissolved, for example, in water. So I would like to thank my Moscow group with who my younger colleagues from Moscow group who did a lot of computer simulations I demonstrated today. I would like especially to thank my colleagues, experimentalists from Moscow State University who did this experiment with gels, so Lena Kozhunova and Galia Komarova. I would like to thank for numerous discussion my German colleagues, Walter Richter and Andrei Pich. And of course, I would like to thank all of you for your kind attention. Thank you very much.